So it's a pleasure to introduce Professor Felix Otto from the Max Planck in Leipzig. He will speak about the thresholding scheme for mean curvature flow and de Giorgi's ideas for minimizing movements. Thank you very much.
Thank you very much, Luigi, for the introduction. It's a great honor to be here and listen and talk with many friends at this conference. So I didn't meet de Giorgi personally. I mean, in terms of academic age, I could have. I did my PhD in '93, but my first visit to Pisa was, I guess, around '99 for an optimal transportation conference which Luigi had organized. So I unfortunately never had the chance to meet him, but I think I grew up, without knowing it at the time, as a PhD student. I grew up in an environment in Bonn which was very much influenced and had the same interests as de Giorgi in his last years, namely gradient flows and minimizing movements. So Fred Almgren was a frequent visitor of my PhD advisor, Stefan Luckhaus. The Almgren-Taylor-Wang scheme was mentioned earlier in earlier talks, and I will come back to it. And next door was Thomas Sturzenhecker, PhD student of Stefan Luckhaus, with whom together they proved a conditional convergence result for the Almgren-Taylor-Wang scheme, so I will come back to that too. And so these ideas were around, and certainly for me quite influential then later on in kind of considering Wasserstein gradient flows and minimizing movements there. Okay, so this being said, but I also think that this conference is certainly a celebration of de Giorgi, but I think it's also a celebration of a very vibrant community, Italian community in the calculus of variations. And I'm very impressed how this community rejuvenates itself in terms of numbers and in terms of quality over years and years. And it's touching to see how members of that distinguished population, wherever they are in Italy or abroad, kind of keep mathematically in touch what's happening at this place. So this place has a lot of importance and responsibility, I guess, for the mathematics, for the type of mathematics we love. So that's also nice to see how de Giorgi's legacy lives on through in this way. Okay, so this being said, what I want to present essentially relies on, let me see whether the pointer works, relies on a joint work with Selim Ezzedoglu a couple of years ago, and then more recent two papers, one not yet posted, one already kind of published with a PhD student of mine, Tim Laux, who kind of is a very strong PhD student who will be on the market this year. So what Selim Ezzedoglu and I started looking at a couple of years ago was kind of a very successful numerical scheme for motion by mean curvature flow, which was invented by Merriman, Benz, and Osher already many years ago, and which really is a computational scheme. So in principle, it's a fully discretized scheme for mean curvature flow, but here I only give you the time discretization part of that scheme, because that's the most important part, and that's, in a certain sense, also the most interesting part. And so like in discretizations, there is a time step size, which I call h, and chi is the characteristic function of the set, the boundary of which evolves by mean curvature. And the scheme proceeds as follows. So you're given the shape as encoded by the characteristic function at the time step n-1, so at the time n-1 times h, if you want. And it proceeds by splitting a time step in two operations. The first part of the operation is a convolution, where you take the characteristic function and you convolve it with the heat kernel at time h. So, which of course in the Euclidean setting is the Gaussian of variance H, so very simple convolution, nice convolution kernel. So you carry out this convolution, then of course you get a perfectly smooth function, which I call UN, and then you ask yourself, where is this function larger than 1/2 and where it is less than 1/2? So you look at the super level set of that function with respect to the value 1/2, that is a new characteristic function, and that gives you, that describes the set at time step size n. So as kind of indicated in this one-dimensional picture, and it's intuitively clear, and I'm going to show you some numerical simulation, that at very exposed parts of the original, of the set at time step n-1, the convolution will recede a little bit so that the new set will have moved a little bit inwards. And on the other hand, if the complement is exposed, it moves in the other direction. So intuitively, it already points the right way. Let me, for this audience, I couldn't refrain from making the remark that, of course, on a metric measure space, you can define the diffusion. So this discretization is extremely robust. You could make sense of it without any differential structure. But I think so here is kind of the outcome of an easy numerical simulation. We start with this dumbbell shape. So that picture represents the characteristic function. Black is 1, white is 0. We take the convolution, so of course we get grayscales because of the modification. This black line is the level set where the convolved function is equal to 1/2. And that's the outcome, and you see that the next, I mean, 2 dimensions, or for curves, there is no singularity formation. So you see that the necks have moved a little bit outwards, right? So you see already, in a sense, the effect of curvature. And the reason why this scheme is so successful numerically is that both steps are numerically of low complexity. Because many of you will know that after spatial discretization, which is straightforward here, convolution can be carried out in a very fast manner by the so-called fast Fourier transform. So that makes the scheme so advantageous as a numerical scheme for mean curvature flow, and of course it also has the advantage that you can go through singularity formation. So, not surprisingly, kind of analysts immediately jumped on the scheme, and already a year afterwards, after it was concocted, Craig Evans gave a convergence proof for the scheme, and it's based on a very simple observation, namely the observation that as mean curvature flow, as the limiting motion, the scheme preserves comparison. So if you have 2 sets which at time step n-1 are nested, then clearly you have an inequality relation between the characteristic functions. Since the convolution kernel is non-negative, the Gaussian is non-negative, this inequality is preserved by convolution, and that of course in particular implies the nestedness of the level sets. So the scheme, like mean curvature flow, preserves comparison principle, and as many of you know, there is a weak notion of solution for practically all elliptic and parabolic scalar problems that that satisfy a maximum principle, which goes by the name of viscosity, notion of viscosity solution. So that also exists for the mean curvature flow, and Craig Evans proved that that indeed the thresholding scheme converges to mean curvature flow in the sense of viscosity solution, because it has the maximum principle built in. So that was kind of one of the first analytic works on this scheme. What was interesting, what was important or of interest for Selim Mezidoglu and myself was that there is a straightforward generalization to the multiphase case. And multiphase here means more than 2 phases, so like here 3 phases, in which case you would describe the phase configuration by three characteristic functions that sum up to 1, so define a partition of space. But then you do exactly the same as before. You convolve each of these characteristic functions, and then at a given point in space, you look which of the three functions is the largest, and that's the set that wins. And here you see 2 time steps for this thresholding scheme in the case of 3 phases. And you see, for instance, immediately that already after 1 step, you get the right angle condition at the triple junction. So people in grain growth know that this is an important condition, and that's instantly, as it should be, kind of satisfied by the scheme. And after a while, you also see the relaxation of the boundary curves to straight lines. And it has been shown or demonstrated by Matt Elsey, Selim Esedoglu, and Peter Smirka that you can this scheme cannot just use for cannot be, efficiently applied to 3 grains in the 2-dimensional case, but to thousands of grains in the 3-dimensional case. You can really simulate these dynamics, which David Kindelera spoke about yesterday, I'm sure, although I had to miss the talk, and which is kind of a crucial process in material science. So again, the scheme, even in the multi-phase version, even for thousands of grains, is doable and competitive. And on the analytic side, very recently, by Yoshito Negawa and his collaborators, it has been shown that that there is at least a notion of solution, a Bracke notion of solution in existence, result for multi-phase mean curvature flow. So there's also on multi-phase mean curvature flow, there's also interesting recent progress. So we asked ourselves 2 issues, 2 questions. The first one, and that's important for the application in grain growth, how can we generalize the multi-phase thresholding to a situation where every interface has a different surface tension? So not just every grain has its energy, but every interface potentially has a different surface tension, which comes from a different mismatch between the lattice orientation of the grains. So that's really something you would like to, a minimal thing you would like to have in the applications. So the question was, how can you adapt this scheme to deal with this more general situation? And that was something people had been interested, and there had been attempts of doing that within thresholding, which perhaps weren't that convincing. And then, of course, the question which I want to dwell on a little bit more here, can we prove convergence in the multi-phase case where there is no comparison principle and where the notion of viscosity solution doesn't apply? Can we prove convergence of the scheme? And indeed, at least in the conditional sense, we can do. We have 2 different types of convergence results, and especially the second one, which I want to present here, has a close connection with ideas of DeGiorgi, but I come to that later. And so the interesting thing is that the starting idea for giving an answer, a positive answer to both questions, is that in this paper with Selim Esedoglu, we figured out that this thresholding scheme has a minimizing movement interpretation, which is very easy to see, and was kind of surprising that it had not been discovered before. So if you want this thresholding scheme, not only, and that's very obvious, preserves the comparison principle of the limiting mean curvature flow, but it also respects, in a certain sense, the gradient flow structure of mean curvature flow, which of course is a crucial feature of mean curvature flow. So let me on the next slide explain to you how you see that, at least in the equal surface tension case, how you see that this thresholding scheme, this very simple and numerically potent scheme, can be seen as a minimizing movement scheme. So So here, it essentially follows from three observations. So in order to make sense of a minimizing movement scheme, you need an energy functional and you need a notion of distance on configuration space. Those are the two ingredients. And so the energy, the relevant energy, is this functional here. So I've written it down already in the multiphase case, where you consider the product of the characteristic functions which define the partition with the mollified characteristic functions, and you look at all different pairs. So if there were not the mollification, the product of chi I and chi j would be 0, but due to the mollification, a little bit of the mass which sits in this characteristic function kind of is smeared out in the support of that characteristic function. So therefore, this integral is positive, but you have to kind of magnify the integral by factor 1 over square root of h. Square root of h is the relevant length scale here to see something. And so that's an energy on characteristic functions, which is known, and it's easy to see, to gamma converge to the sum of the interfacial length between the phases I and j, which here I've written in this somewhat fancy BV fashion, which of course all of you are very familiar with. So on the one hand, you have this energy functional that as h goes to 0, h was the time step size, gamma converges to the total interfacial energy, which is the right limiting energy for which the motion by mean curvature flow is the gradient flow. Then the distance is more subtle. So if you look at the same functional, but now you plug in the difference of two characteristic functions, and you put a minus sign in front of it, then you can rearrange it in this way using the fact that the characteristic functions sum up to 1, and using the semi-group property for the heat kernel, you can rewrite it as clearly a positive definite expression. So minus this energy function applied to the difference of two configurations is the square of a norm. So it has the feature of the square of the norm, so can be seen as distance squared if you want. And then it's a very simple observation which has just to do with kind of quadratic expansion, that if you look at the bilinear form which comes with this quadratic functional, so which I denote like this, and you expand it, you can write it like this up to a constant term. And on the one hand, it's immediately clear that thresholding means minimizing this functional. So because that just means looking where the convolution of this function is largest, or which of the components is largest. So the left-hand side is thresholding, and the right-hand side can be interpreted as having the structure distance squared plus and minimizing distance squared plus energy. So it's a very simple observation which shows that this thresholding scheme has the structure of a minimizing movement scheme. So in a certain sense, it not just, as I said in the beginning, preserves the comparison principle, but also kind of respects the gradient flow structure of mean curvature flow. But with a twist, like in Sandy-Serfati, there is a gamma convergence of the energy functions involved, but it has this up to that twist. It has the right structure. So on the one hand, but I don't want to go into details here because I think that's not the most important thing for this audience. This structure now allowed us to, without any difficulty, to extend this scheme to the case of different interfacial tensions between the different phases, just by taking the same expressions and smuggling in these numbers. And again, you can show that this gamma converges to the right energy, and in fact there is kind of also a tradition in proving this type of gamma convergence results. And on the other hand, this expression is, at least in the relevant cases for grain growth, is a distance squared. And from this, by the same logic as before, you read off how to set up a thresholding scheme for the multi-phase case with different surface tensions, and it turns out to have exactly the same complexity. So we were quite happy with this because this point of view on thresholding led the right way to come up with this generalization, which has exactly the same complexity as if you had equal surface tensions. So that, that's the first result. That's the result of the paper with Selim Ezedoglu. But what I really would like to talk a bit more about are the two papers with Tim Laux, where we consider the question of convergence, because there is a clear, at least for the second paper, a clear connection to De Giorgi's ideas. And although we can prove the result in the general case for n phases and general interfacial energies, I'm going to give you the statements and sketch the proof only in the case of two phases in order to avoid notation and make the ideas clear. So the main challenges are in the proof are already present in the two-phase case. So in the two-phase case, again, this is the energy functional. So you have just a single characteristic function that describes your set. And as I described before, you're looking at the product of the complement of the characteristic function with the convolved original characteristic function. So only because of the smearing out of the convolution, this integral does not vanish, is positive, and you look at you magnify its value by 1 over square root of h, which by parabolic scaling, of course, is the length scale of the Gaussian. So essentially, the size of the support of this convolution kernel up to exponential tails or Gaussian tails, and the typical question you would ask, like always, is you're given some initial data on which the energies are bounded. So in other words, for which the parameter is finite, you plug this into your minimizing movement scheme or the thresholding scheme, which is a minimizing movement scheme. You get a sequence of characteristic functions. You interpolate them, let's say, piecewise, constant in time on these time intervals of size h. And then you're asking whether this function of time and space converges in some sense to a characteristic function that evolves by mean curvature. So that's the natural convergence result. And now I want to present two results we have in this direction, which both are conditional convergence results. So they come with a defect which has a good tradition. So I'm going to explain to you why they're just conditional convergence results, and but that we're in good company in having just a conditional convergence result. And the first convergence result is, in fact, the one which is harder to prove, and that's a convergence result to mean curvature flow in the sense of BV. And the second result, and this is the one I want to speak more about, is a convergence result towards a Brachet-type solution. And I want to speak more about this because that's the one that involves ideas from De Giorgi. And in fact, it's much softer. So here's the first result. So the one which was already around a year ago. So let's suppose that this after passage to subsequence, the sequence of characteristic function converges strongly in space and time, let's say L1, then of course it would also converge in any LP. That's not a big assumption. There is certainly enough compactness to guarantee this type of convergence for any subsequence. But the important assumption, and this is why it's only a conditional convergence result, is that the energies, the approximate energies when integrated in time, converge to the limiting energy when integrated in time. And that's an assumption which you don't get out of a priori estimate, the available a priori estimates. It in particular implies that there are no ghost interfaces, there's no touching of interfaces. So that's a restrictive assumption. And of course, I mean, one inequality comes for free. I mean, the limit is always less than the lim inf of this one from gamma convergence, but asking for the equality is really an additional assumption. But anyway, so under this additional assumption, which makes it a conditional convergence result, we get mean curvature flow in the BV sense. So there exists a normal velocity, which is a square integrable function on the interface, which is characterized distributionally as you would characterize a normal velocity, such that mean curvature is equal up to a factor of 2 and a minus sign to normal velocity. And as you would do, you write mean curvature in this, let's say, varifold way. So you do an integration by parts in order not to have to write down mean curvature in the classical way. So in this sense, we get this, this conditional convergence result. So let me say that we're in good company when it comes to this result. So here again is this additional assumption we're making, and here is the notion of solution, because this additional assumption and the notion of solution is exactly the same as in the important paper by Luckhaus and Sturzenegger, which was done next door at the time. I mentioned that at the beginning of my talk. And, but they didn't work on the thresholding scheme, but they did that for the so-called Almgren-Taylor-Wong scheme for mean curvature flow, which was already mentioned in a couple of talks, and which I think was a crucial concept for minimizing movements introduced at the time. So in '93, Robert Almgren, Gene Taylor, and Li Wang introduced that scheme, and gave also some conditional convergence result, but that then was very much improved by Luckhaus and Sturzenegger. And we're doing the same thing, not on, if you want, this academic scheme, but on this very robust numerical scheme. And it turns out that, that in fact, also our proof is a bit more robust. So as opposed to Luckhaus and Sturzenegger, we in fact do not need regularity theory for almost minimal surfaces. So our result is not restricted to dimensions less than 8. So, so our tools here are a bit more robust, and perhaps at the end I have to have the chance to say a little bit about this. But the story I want to tell you is now kind of a closer connection with ideas of de Giorgi, and that came around because we were asking, well, I mean, so with Selim Esedoglu, we kind of found this minimizing movement interpretation of thresholding. With Tim Laux, there is this convergence proof. But if you make already this connection to gradient flows, you should be at least able to get an energy inequality in the limit. But the energy inequality does not follow from this notion of solution. There is no at least I don't see how to get the energy inequality from this notion of solution. It's too weak. So, so we were asking at first the question, you know, can we also get the energy inequality? Here I've written it down. So there's a minus sign missing. So all the way everywhere there are minus signs missing. I'm sorry for that. Is the dissipation, so the square integral of the mean curvature or the square integral of the normal velocity, there's a factor of 2 because of our normalization, is that estimated by the rate of change of the energy? And when asking this question, we reminded ourselves that there are, in a certain sense, two notions of gradient flows or formulations of mean curvature flow that have this energy inequality in a certain sense built in. There is de Giorgi's formulation of gradient flows, which in particular yields the energy inequality, but which is written in such a way that it not only yields the energy inequality, but on smooth solutions, on smooth configurations, it's in fact equivalent to mean curvature flow. That's one approach. But then there is also this notion by Brachet of mean curvature flow, which in a certain sense is somewhat similar in the sense that it also tries to enrich the energy inequality in such a way that it contains the entire notion of solution. And it does so by localizing the energy inequality. So instead of monitoring the rate of change of the total interfacial area, you're monitoring the rate of change of a localized interfacial area localized by this non-negative function zeta. And then, of course, you get one term, which is just the localized dissipation. But, of course, you get another term, an additional term, which depends on the gradient of the localizing function. But the nice thing for Brachet is that both of them can be both of them can be expressed in terms of the mean curvature. So he gets his formulation has the advantage that it gets completely rid of the normal velocity. And of course, typically it's not formulated in the BV setting as I'm doing here, but in the varifold setting. But anyway, we're working here in the BV setting, so I've given you the formulation in the BV setting. So, therefore, now the idea is, so what we're going to do is proving kind of convergence, still conditional convergence to this notion of solution, and, but using ideas of de Giorgi to do that. So here is kind of the second result, which we still have to post, but it's ready. So again, the same conditional convergence assumption, and but now convergence towards the notion of Brachet as Brachet type, because we express it. I mean, we're doing a poor man's version because we're working in the BV context instead of the more natural varifold framework for Brachet. So that's just the weak formulation of saying that this function h is the mean curvature, and then this is really Brachet's inequality that encodes mean curvature flow. So now in the remainder of my time, I would like to tell you how, in order to prove this, we're using ideas of de Giorgi in the context of minimizing movements. So, but I think I have one more slide on Brachet, or the difference between the BV formulation and Brachet formulation. So if you want the BV formulation, the weak BV formulation relies on two formulas. It relies on the formula defining, in a certain sense, which you use to define the normal velocity by monitoring how does the integral of a function over the bulk change in time. And it relies on the usual integration by parts formula for mean curvature with a tangential divergence of some vector field. Whereas Brachet's solution encodes the normal velocity in a different way. Instead of monitoring the rate of change of a bulk integral, it monitors the rate of change of a surface integral. So it's much more in the spirit of looking just at the interfaces, at looking at the networks in the multiphase case, instead of looking at the bulk, at the sets themselves. So that's from a classical point of view, that's the main. That's one of the main differences between these two ways of encoding mean curvature flow. So BV sees in and out, and Brachet kind of doesn't really see the orientation and focuses more on the internet, on the interface. So I said that that in order to get to Brachet's solution, we're using ideas of de Giorgi, and the ideas of de Giorgi we're using were already kind of prominent in this conference. So and we know them from the monograph of Luigi Ambrosio, Giuseppe Savary, and Nicola Gili, where this is all worked out. And I spoke with Nicola. He told me that okay, there is a paper or there are notes by de Giorgi, but in fact there are many new ideas in what's in the book. So I'm referring here to what I know from the book. So many of you, so the starting point is an abstract minimizing movement scheme for gradient flow, where you minimize one half times time step size, distance squared to the previous time step plus energy. That's your minimizing movement scheme. And everybody who has worked with minimizing movement knows that there is an easy a priori estimate for which you don't have to work at all, which just means you compare to the previous time step and you add this up. And when you add this up, you get a wonderful a priori estimate, which gives you all the compactness which you want. Namely, it gives you sup bound on the energy, and it gives you an L2 bound in time on the dissipation by the initial energy. And that's extremely powerful and gives you kind of a lot of leeway. But if you formally pass to the limit in this equation, because of the 1/2 here, which is sitting here, it doesn't turn into the right energy inequality. It misses the right energy inequality by a factor of 1/2. That's the big, often this is not the problem, but when you're dealing with strongly nonlinear problems like P-Laplacian or so, getting the right energy inequality is a crucial step in getting the right existence proof. So this is kind of a major problem that the 1/2 is sitting there. So you want to get rid of this 1/2. And here comes the idea of de Giorgi. So he introduced a different type of interpolation between the time steps. So instead of doing this boring piecewise constant interpolation, he said we have to interpolate between the time steps in a smarter way in order to recover this factor of 1/2. And we have to use the problem itself to interpolate between the previous time step, so chi n minus 1, and the new time step chi n, by changing the prefactor in front of the distance. So if the time is very close to the previous time step, you put a huge number in front of this, so you're staying very close to chi n minus 1. But as your time moves to the next time step, you're recovering the usual minimizing, the original scheme. So that's a way of interpolating. And the big advantage of interpolating like this is that you recover the missing factor of 1/2 in this inequality with help of the metric slope, which kind of is a kind of the norm, the Euclidean norm or the right notion of norm of the size of the gradient, which again you define completely intrinsically in terms of the distance function. And now thanks to this more subtle term, this inequality here at least formally converges to the right limit. So that I think is the key idea the key idea from Ambrosio Gili Savare, which we're using here, and which comes extremely handily. So I mean, we were surprised how handily this comes. But now there is a twist. So we want to converge to Brachet. So we don't want just to recover the energy inequality, but we want to recover the localized energy inequality. So so that's the localized energy inequality. We have to work with this localizing function zeta. But the minimizing movement scheme doesn't see a localization. It's a global variational problem. So there we were lucky, or in a certain sense, again, it shows that this thresholding scheme is a very nice scheme. You can localize it as a variational problem. So in other words, the thresholding scheme does not just satisfy a single minimizing movement scheme, but it satisfies a whole family of minimizing movement schemes, and that's what we're using to our advantage. So not only does it satisfy what Selim Esedoglu and I observed, but it satisfies a localized version. So we can put a localizing function in the energy. We can put a localizing function in the dissipation. Of course, that wouldn't be true. So what you get correction terms, and the correction terms, not surprisingly, involve the commutator between convolution, which is kind of the only non-local operation here, and multiplication with the localizing functions. And it's this first commutator term which gives rise to the transport term in Brache's formulation, and there's a second commutator term which comes from smuggling in the zeta here, which vanishes in the limit. So not only do we have a single variational minimizing movement scheme, but we have a whole family of minimizing movement schemes, which has the only slight twist that the energy is not really an energy, it depends on the previous time step. So, but that's not an hindrance for Ambrosio Gili Savare. You can, despite the fact that the energy functional depends on the previous time step, you can do exactly what we learned from De Giorgi. You can look at the variational interpolation, you can look at the metric slope, and you get the inequality. So the fact that the energy also depends on the previous time step is no difficulty for this setup. And so how much time do I still have? 10 minutes. So I don't have to rush, but on the other hand, I don't have to finish on time. I don't have to finish. I may finish before time. So here, so a little bit of details. Here is the kind of this modified energy functional, which we get through the localization, which involves the commutator. Here is the localized distance function, which has very much the same structure as before. Here is what we get from Ambrosio Gili Savare. And now we use of course, now we have to use the specifics of the problem. So the first specifics of the problem is, now all these nice things of this De Giorgi formulation, which kind of leverages lower semi-continuity to its best, comes to our help. So when computing the metric slope, of course we can, it dominates. Looking at the first variation in any direction in function space dominates looking at inner first variations as defined by a vector field psi. So the metric slope controls inner variations and kind of the metric structure of the gradient flow is encoded by the numerator. The differential, so the inner variation which comes here, behaves very well with respect to the localization. And this additional term, which involves the commutator, in fact, can be easily recognized as being the differential of the metric term, which by the Euler-Lagrange equation of minimizing movements is related to the differential of the energy. So, so with these three observations, which are now, of course, problem-specific and no longer kind of abstract gradient flow theory, which again I've written here, you've gotten a step closer to Brache's formulation. And now what you see is that in the end, only two expressions, you have to pass to the limit only in two types of expressions, in the expression which involves the second derivatives of the Gaussian convolution kernel and the Gaussian convolution kernel itself. And those are the only expressions in which you really have to pass to the limit. And it is there where we use the convergence assumption. So identifying the limits for different kernels by related expressions, that's the only place where we use the convergence assumption. And of course, it's very tempting to use varifolds to circumvent this problem, but so far we didn't. We have no idea how to do that. Okay, so last slide, last one or two slides. So that was kind of the main idea for the second result. So the convergence towards Brache's solution and using ideas of De Giorgi, kind of making the connection between his abstract treatment of minimizing movements and Brache's localized encoding of mean curvature flow through the localized energy inequality. And now I want to just say that, so this is extremely soft, and that's probably kind of the power of the ideas of De Giorgi, that they allow you this very soft treatment. The other result, this BV convergence, this convergence to the BV notion, in fact, is much harder. Like Luckhaus-Sturzenegger, one has to work to pass to the limit in the first variation of the metric term. And there you're confronting kind of the standard issue in analysis that in principle you would like to use that weak convergence times weak convergence is still convergence, which of course is not true. And that's the main problem. You have one term that converges weakly to the distributional normal velocity, and you have another term that should weakly converge to the normal, but you want to pass to the limit in the product, and you can't do that. So the idea to do that is kind of standard, I would say, in geometric analysis. You want to first replace this approximation to the variable normal by fixed normal, using that the limit is close to a half space. So in other words, you introduce a notion of excess, which is well known in kind of minimal surface regularity, where you look at the excess energy of your limiting interface. Well, here it's still on the level of H, but here it's on the limiting interface with respect to a half space. And that's where you need the convergence assumption. You need the convergence assumption to get that the excess on the level of H converges to the limiting excess, which then by soft results on the BV structure you can show is small after localization. So the main idea is to use bounds on the dissipation to control the first factor, and to use excess to control the difference between the second factors to pass to the limit here. And there's one point which is non-soft, where we really have to go back, where it's not enough to just look at the first variation of the thresholding scheme, but where we really have to go back to the thresholding scheme when it comes to estimating the time derivative of these characteristic functions, getting a good estimate of the time regularity down to time scales which are small compared to one of the two intrinsic time scales, which is square root of h, which is also the spatial scale. And for that, we need one estimate, elementary estimate, but which uses again kind of the specifics of the scheme, which I don't have the time to address here. And so that brings me to the end. So clearly there is, I mean, both Tim, perhaps he more than I, finds the fact that we just have a conditional convergence result a little bit unsatisfactory. And especially now with this very weak notion of Brache varifolds, it might be, it's very tempting to try to prove that one has an unconditional convergence proof towards that notion of solution. And perhaps one may learn from the recent existence result for the limit in that direction. But so Yoshito Negawa visited a couple of months ago. We didn't right away see how to do that. That's from the point of view of analysis, and from the point of view of applied math. For those people who know grain growth, and after David's talk, I think we all know a bit more about grain growth. Of course, you should not just look at an interfacial energy that depends, I mean, that's different from grain pair to grain pair, but it should also be anisotropic. So in fact, you would like to come up with more anisotropic versions of this. And clearly there is something which can be done for the thresholding scheme. There's work by Chambol and co-workers, and Selim Esedoglu has now recent work where he kind of extends as much as possible our minimizing movement point of view also to the anisotropic case. Okay, so that's it. Thanks for your attention.
Thank you. I was wondering whether in this very nice thresholding scheme, is there something that reproduces into the limit when you are able to prove convergence to some notion, like bracket notion of mean curvature flow, to reproduce the monotonicity formula, like a Whisker monotonicity formula, and this kind of tools which are...
I think that might be one of the key difficulties that, so this thresholding scheme, like Ungrain Taylor-Wong scheme, has its own characteristic length scale, which is square root of h. And I think getting monotonicity formulas on scales which are large compared to h is fine for both schemes. And the very small scales are no problem, especially in thresholding. The crucial step would be to get something of the type of a monotonicity formulas which carries you across the scales of order of square root of h. And that we didn't see. In Brache's existence proof, which is very much kind of by which the work by Tonegawa and Kim is very much inspired, he works with two different length scales. There is one length scale which comes from the convolution, and which allows him to jump in time, and they're apart. And playing with these two length scale, he's able kind of to bridge this. Whereas if you start with a specific, if you're given a scheme like Ungrain Taylor-Wong or thresholding, there's a single length scale, and it's not clear at least not clear to me how to do that.
More questions, comments? Well, I have also a question. Is there an implication, without referring to approximations, from, let's say, a notion or solution in the sense of the Giorgi, the one you presented with the sum of two squares with 1/2, to Brache, or is it possible to establish a connection? Or?
That's a very good question. I'm probably not the best expert to answer that question. So in a certain sense, one of the merits of Brache is that he gets, the entire formulation doesn't see the normal velocity, which of course is very prominent in De Giorgi's formulation. So yeah, the short answer is I don't know. It's a good question, I don't know.
Any more questions? Okay, so if not, let's thank Felix again.